The Bottleneck of Steel, December 12, 1941, Cleveland, Ohio. The air inside the Republic Steel plant is thick with the acrid stench of sulfur and the deafening, rhythmic thud hiss of hydraulic presses. Outside, the world is still reeling from the smoke of Pearl Harbor. But inside, the war is being fought with fire and iron. Arthur J. Raymond, an industrial consultant with a sharp jaw and a grease-stained tie, stands on the catwalk, peering down at the floor. His eyes aren't on the grand machinery, but on a pile of discarded 155mm shell casings, distorted, cracked, and useless. Beside him, Foreman Grizzly Joe Miller wipes a blackened hand across his forehead. It's a damn funeral pyre. Artie, Joe bellows over the roar of the furnaces. We're throwing away 3 out of every 10 shells. The steel either comes out soft as butter or brittle as glass. If the Army wants 1 million of these by spring, they better start praying for a miracle, because we're making junk. Arthur watches a veteran blacksmith, a man whose father likely forged horseshoes, carefully lifting a glowing red shell casing with long tongs. The smith plunges it into a vat of oil, his eyes squinting to judge the correct shade of cherry red before the quench. It is a scene out of the Middle Ages, an artisan-level craft where a man's intuition determines whether a piece of steel will pierce a panzer or shatter in the breech of an American gun. It's too slow. Joe, Arthur mutters, pulling a silver stopwatch from his pocket. He clicks it as the smith begins the tempering process. You're treating every shell like a custom-made sword. At this rate, the boys in the Pacific will be throwing rocks at the Japanese. Arthur descends the iron stairs to the foundry floor, his leather shoes clicking against the soot. He picks up a rejected casing. The steel is uneven. In some spots, the molecular structure has locked into a hard, unyielding matrix. In others, it remains dangerously pliable. The problem isn't the steel itself. It's the heat. The traditional batch method, where shells are shoveled into a furnace like loaves of bread, results in uneven temperatures. The shells in the center stay cool. The shells near the walls burn. He looks at the furnace, a massive, brick-lined beast. It takes 6 hours to heat a batch, 2 hours to quench, and another 4 to temper, 12 hours for a handful of shells. Meanwhile, the War Department is screaming for the great arsenal of democracy to wake up. Joe, Arthur says, pointing to the massive, glowing furnace. We have to stop cooking the steel. We have to start managing it. If we can't find a way to make every square inch of that casing hit the exact same temperature at the exact same second, we're going to lose this war in the factory before we ever lose it on the battlefield. He walks over to a blueprint table, clearing away coffee tins and tobacco pouches. He doesn't see a factory. He sees a series of thermal variables. He realizes that the bottleneck isn't the metal. It's the clock, and the clock is ticking faster than the American war machine can turn. The Radical Observation, January 14th, 1942. The War Production Board Office, Washington, D.C. The humidity of the Potomac hangs heavy over the Capitol, mirrored by the suffocating atmosphere inside the windowless boardroom. Arthur Raymond sits across from a row of stone-faced colonels and executives from the big steel conglomerates. On the table between them is a single, cross-sectioned 150mm artillery shell. It has been etched with acid to reveal the crystalline structure of the metal, and it looks like a chaotic mess of jagged shards. The current failure rate is 40% across the entire Ohio Valley. Mr. Raymond, Colonel Thomas Vance says, tapping a swagger stick against the table, we have ships sitting empty at the docks in Norfolk because we don't have enough ordnance to fill their holds. Every hour you spend consulting is an hour our boys in the Philippines spend undergunned. Arthur leans forward, his hands clasped tight. The problem, Colonel, is that your manufacturers are treating steel like a living thing. They talk about the soul of the metal. They wait for the right color, and that's fine for a village smithy. But we need an ocean of fire. We are losing time in the cooling phase. He slides a piece of graph paper across the table. It isn't covered in chemical formulas, but in a simple timeline of temperature. I spent 72 hours straight at Republic Steel. I noticed that the artisans spend 90% of their time waiting for the furnace to reach equilibrium. Then, They spend another hour arguing over whether the quench oil is too hot or too cold. And your solution? A Bethlehem Steel executive asks, his voice dripping with skepticism. Heat is heat. You can't rush physics. You can't rush physics. But you can automate it, Arthur retorts. I watched a woman at a local bakery last week. She wasn't checking the color of her bread. She was using a conveyor belt that moved the dough through a tunnel of calibrated heat. Every loaf came out identical because the environment was constant, not the ingredients. He stands up, pacing the small room. We need to stop batch heating. We need to create a thermal tunnel. We move the shell casings on a continuous chain through induction coils instead of heating the air around the shell. We use electromagnetic induction to heat the shell itself from the inside out. We can bring a casing to 1500 degrees Fahrenheit in seconds, not hours. The room falls silent. Induction heating was a laboratory curiosity, used for small precision parts, not for multi-ton industrial shell production. To scale it would require tearing out millions of dollars of existing furnaces and replacing them with unproven electrical coils. The time savings would be astronomical, Arthur continues, his voice rising with conviction. By standardizing the heat treatment into a continuous flow, we cut the cycle from 12 hours to less than 45 minutes. We eliminate the artisan's guess. A high school girl with 2 days of training can run the line better than a master smith because the machine doesn't have an opinion on the color of the steel. Vance narrows his eyes. You're talking about an assembly line for the very molecular structure of the weapon. If the calibration is off by even a fraction, we produce 100,000 bombs that could explode in our own faces. If we don't do this, Arthur says, looking the colonel in the eye, we won't have any bombs at all to worry about. Arthur leaves the meeting with a temporary experimental rating and a budget that barely covers the copper for the coils. He heads back to Cleveland, not to the front office, but to a small, grease-stained workshop in the back of a machine shop. He knows that the small observation of a bakery conveyor belt is about to collide with the massive, stubborn weight of American industry. If he can make one shell perfectly in 45 minutes, he can change the world. If he fails, he's just another civilian who got in the way of the war. The birth of the thermal tunnel, February 18, 1942, a makeshift laboratory, Cleveland, Ohio. The smell of ozone is sharp enough to sting the back of Arthur's throat. The workshop is a chaotic web of heavy-duty electrical cables, copper tubing, and cooling water pipes. In the center of the room stands the prototype, a series of coiled copper rings, looking more like a rib cage than a weapon of war. Arthur adjusts his spectacles, his fingers trembling slightly as he dials the frequency on a massive, humming transformer. Powering up, he shouts to Joe Miller, who stands behind a protective plexiglass shield, clutching a fire extinguisher. A dull, low-frequency thrum begins to vibrate the very floorboards. Arthur slides a cold, dull gray 150-millimeter casing into the center of the copper coils. There is no fire, there is no smoke. But within seconds, the air around the shell begins to shimmer. The steel doesn't just get hot. It begins to glow from within. A deep, bruised purple transitions into a vibrant, sun-bright orange in less than 60 seconds. Look at that color. Artie, Joe yells. It's perfect. It's uniform. No cold spots. Arthur clicks his stopwatch. 64 seconds to reach the critical transformation temperature. In the old batch furnaces, this would have taken hours of soaking the metal. But the induction coils are vibrating the iron molecules themselves, creating heat through friction at an atomic level. Suddenly, a hydraulic arm kicks in, sliding the glowing shell out of the rib cage and directly into a high-pressure spray ring, instead of a plunge into a stagnant vat of oil, which often created air bubbles and soft spots. Arthur's design uses a precision quench. Dozens of nozzles blast the shell with a calibrated volume of cooling fluid at a specific pressure. Hiss! A cloud of steam erupts, filling the room with a white veil. As the mist clears, the shell casing sits in the cradle, dripping and dark. Arthur rushes forward with a Rockwell hardness tester. He punches the diamond-tipped needle into the base, the midsection, and the nose of the shell. 28, 28, 29. Arthur breathes, reading the dial. He looks at Joe, a grin breaking across his face. It's a mirror. The hardness is identical across the entire body. No artisan intuition required. But the true test isn't just one shell. Arthur looks at the conveyor belt he's rigged up. A crude, bicycle chain-driven system. Load the next one. Joe. And don't stop. For the next 8 hours, they run the thermal tunnel. One shell every 90 seconds. No waiting for furnaces to reheat. No batch downtime. By midnight, the floor is stacked with 200 shells, each a perfect molecular clone of the last. Arthur leans against the workbench, his shirt soaked in sweat and grease. He calculates the math on a scrap of cardboard. One line, running 24 hours a day, could produce nearly 1,000 shells. 10 lines could outproduce the entire pre-war output of the United States. We've done it. Joe, Arthur says, staring at the mountain of steel. We've taken the art out of it. We've turned a blacksmith's secret into a grocery store's inventory. The next morning, the report is hand-delivered to the War Production Board. It isn't a plea for more money. It is a death warrant for the old way of making war. The small observation from the bakery has been forged into a thermal scythe, and the bottleneck that threatened to starve the Allied guns is about to be shattered forever. The tsunami of steel. May 22, 1942. The Pentagon, Arlington, Virginia. General Brian Somervell, the man responsible for the Army's entire logistics tail, stares at the production chart pinned to the wall. For months, the line representing projected ordnance needs had been a steep, terrifying mountain, while the actual production line had been a flat, pathetic crawl. But in the last 30 days, something impossible has happened. The production line has spiked vertically. It isn't just growing, it's exploding. Who did this? Somervell asks, his voice low. I was told we were 6 months behind on 150mm ammunition. Now I'm being told we have so many shells, we're running out of wooden crates to pack them in. Colonel Vance steps forward, dropping a heavy, dark gray casing onto the general's desk. It's the Raymond process. Sir, that consultant from Cleveland. We gave him one wing of the Chrysler tank plant in Detroit to set up a full-scale induction line. He didn't just meet the quota, he obliterated it. Vance opens a folder, revealing photographs of the new assembly lines. They don't look like foundries. They look like gleaming laboratories. Long rows of glowing copper induction coils hum with a high-pitched whine, while shells move through them on a continuous, automated track. The old batch furnaces produced roughly 50 shells a day with a 40% scrap rate, Vance explains. Raymond's thermal tunnel is running 24 hours a day. Each line is spitting out a finished, heat-treated shell every 60 seconds. His scrap rate is less than 1%. You can almost hear the gears of the global war shifting. The bottleneck hasn't just been cleared. The drain has been widened into a canyon. This small observation regarding the heat treatment process has effectively cut the manufacturing time by 90%. What used to take a half day of artisan labor is now a 1-minute mechanical transaction. What about the quality? Somervell asks, running a finger over the smooth, perfectly tempered steel, better than the hand-forged ones. Sir, Vance replies, because the heat is generated inside the metal by electromagnetic friction. The core of the shell is just as strong as the skin. These shells won't crack in the cold of the Aleutians or soften in the heat of North Africa. They are perfect clones. By the summer of 1942, the Raymond process is being exported to every major factory in the American Midwest. The arsenal of democracy is no longer a slogan. It is a physical reality that the Axis powers cannot comprehend. In Berlin, Albert Speer is struggling to squeeze more labor out of occupied Europe to man traditional furnaces. In Detroit, a housewife who had never seen a piece of industrial steel a month ago is now supervising an induction coil that produces more artillery in a week than a German village produced in a year. Arthur Raymond stands on the floor of the massive Chrysler plant, his suit jacket off, his sleeves rolled up. He watches the steel tsunami. A shell enters the coil cold, turns incandescent orange in 60 seconds, flashes into steam in the quench, and rolls out toward the packing crates, all without a single human hand touching the metal. He looks at his stopwatch one last time. It's no longer about whether they can make enough. It's about how fast the ships can carry this mountain of steel across the Atlantic. The art of war has been replaced by the science of the assembly line, and the Axis is about to be buried under the weight of an innovation they never saw coming. The Reign of Iron, August 15th, 1944, near Falaise, France. The earth doesn't just shake, it liquefies. From a ridge overlooking the valley, a German Oberst colonel of the 7th Army grips his trench periscope until his knuckles turn white. He has survived the Eastern Front, but he has never seen anything like this. This isn't a barrage. It is a literal, unending rain of iron for 3 hours. The Allied artillery has been firing with a sustained rate that defies every German manual on logistics. They should have run out by now. The Oberst screams over the thunder. No army can move this much ammunition. Where is it coming from? He doesn't know about Arthur Raymond. He doesn't know about the induction coils in Detroit or the bakery-inspired conveyor belts in Ohio. He only knows that for every shell his own guns fire, the Americans fire 20. He only knows that his men are being buried under millions of tons of high-grade steel that is so perfectly tempered it never misfires, never cracks, and never fails to obliterate its target. Back in the United States, the scale of the achievement has become staggering. The standardization of the heat treatment process didn't just speed up production. It allowed for a massive diversification of the workforce. Because the art of the blacksmith had been replaced by the calibration of the engineer, over 100,000 workers, many of them women who had never set foot in a factory before, were now producing world-class ordnance in a small office in Cleveland. Arthur Raymond reads a classified cable from the front lines. It details the time on target TOT barrages, where multiple batteries fire at staggered intervals so that all their shells land at the exact same second. Such a tactic requires thousands of shells with identical ballistic properties, shells that only the Raymond process could produce in such volume. They're calling it the Steel Rain. Artie, Joe Miller says, dropping a newspaper on Arthur's desk. The headline reads, "Allied Guns Silence the Western Front." Arthur looks at the photo of a mountain of empty brass and steel casings in a French field. He doesn't see the destruction. He sees the efficiency. He sees the molecular structure he fought to stabilize. "We didn't just give them more shells, Joe," Arthur says, his voice quiet. "We gave them the ability to trust the metal. We turned a bottleneck into a floodgate." The small observation was now a global reality. The 90% reduction in production time had effectively shortened the war by months, perhaps years. The Axis powers, built on the myth of superior engineering and artisan skill, had been crushed by the superior logic of the American assembly line. The war of the blacksmiths was over. The war of the machines had been won. The legacy of the induction revolution. September 1945. The Chrysler tank plant, Detroit, Michigan. The silence in the factory is as jarring as the noise used to be. The high-pitched whine of the induction coils has finally ceased, and the massive copper rib cages stand cool and dark. Arthur Raymond walks the length of the assembly line one last time. The floor, once polished by the frantic movement of millions of steel casings, is now being prepped for the return of civilian production. Automobiles, refrigerators, and washing machines. Beside him, Joe Miller kicks at a stray packing crate. The Army sent over the final tally this morning. Artie. Over 250 million artillery shells produced in 3 years. Most of them went through a tunnel like this. Arthur stops at a master control station. He runs his hand over the dials that once dictated the molecular fate of the American front line. Because of his small observation, the United States hadn't just outproduced the Axis. It had redefined the very nature of industrial metallurgy. The induction process he pioneered was already being adapted for the civilian world. For hardening crankshafts, welding pipes, and even cooking food. "We turned the factory into a laboratory, Joe," Arthur says, "and the laboratory saved the world. If we had stuck to the old batch furnaces, we'd still be fighting for the hedgerows in Normandy." The impact was undeniable. By standardizing the heat treatment process, the U.S. had achieved a logistical velocity that no other nation could match. In 1941, it took hours to temper a single heavy shell with a high risk of failure. By 1945, the thermal tunnel could churn out a flawless casing in seconds. This 90% reduction in time wasn't just a statistic. It was the difference between a soldier having 1 shell to fire or 10. Arthur looks out the window at the Detroit skyline. where the smoke of 1,000 factories is beginning to clear. He thinks back to that day in the bakery. The simple sight of a conveyor belt moving dough through a tunnel. It was a civilian's eye, unclouded by military tradition or metallurgical dogma, that saw the solution to the military's greatest bottleneck. The war was won by the generals and the soldiers. Yes, but it was sustained by the men like Arthur who looked at a slow, artisan-level craft and realized it could be an automated flood. The steel rain that had washed over the axis was born from the realization that time, just like steel, could be forged and mastered. Arthur Raymond picks up his briefcase and heads for the exit. He isn't famous. His name isn't in the history books alongside Patton or Eisenhower. But every time a veteran speaks of the overwhelming American fire superiority that saved his life, they are unknowingly speaking of the man who looked at a loaf of bread and saw a way to save a civilization. The Blueprint for Peace, October 12, 1945, Massachusetts Institute of Technology, MIT. Arthur Raymond stands before a chalkboard, not in a grease-stained apron, but in a crisp academic suit. The war is over, but the frantic hunger for his data has not diminished. The men sitting in the lecture hall are no longer Army colonels. They are the architects of the post-war boom. Engineers from General Motors, General Electric, and Westinghouse. The lesson of the thermal tunnel isn't about artillery, Arthur says, tapping the chalk against a diagram of an induction coil. It is about the elimination of the variable. We proved that if you can control the thermal environment at the molecular level, you can make steel do anything. You can make it as hard as a diamond or as flexible as a spring. And you can do it 1,000,000 times without a single error. He sketches a new design on the board, a continuous induction hardening system for automotive crankshafts. During the war, we needed millions of shells to destroy. Today, we need millions of cars to build a new life. If we return to the old ways of batch heating and artisan guesswork, a car will remain a luxury for the rich. But if we apply the induction tunnel to the assembly line, the automobile becomes a commodity for every veteran returning from the front. The transition was instantaneous. The technology that had cut artillery production time by 90% was immediately diverted into the American domestic engine. The small observation of 1941 became the standard for the 1950s. Every hardened gear in a family sedan, every tempered blade in a skyscraper's structural steel, and every precisely welded pipe in the new suburban developments owed its existence to the bakery tunnel logic. Arthur looks at Joe Miller, who is sitting in the front row. Joe had traded his foreman's whistle for a consultant's clipboard. Together, they had seen the American manufacturing bottleneck at its most suffocating point, and they had watched it shatter. We buried the Axis under a mountain of iron. Arthur tells the room, his voice steady. But our greatest victory wasn't the steel rain. It was the realization that we no longer have to wait for the metal to tell us what it wants to be. We have mastered the fire. As the lecture ends, Arthur walks to the window. Below him, the streets are crowded with the first wave of post-war civilian vehicle. He watches them move in a steady, synchronized flow, much like the shells on his Detroit assembly lines. The artisan-level world was gone, replaced by a high-velocity, high-precision civilization born in the ozone-scented workshops of the war. Arthur Raymond had turned a bottleneck into a floodgate, and in doing so, he had ensured that the arsenal of democracy would become the factory of the future. The civilian's eye had seen the truth, that the secret to winning a war and building a peace is simply finding a better way to manage the clock. The atomic structure of victory. December 1946, a research laboratory in Pittsburgh, Pennsylvania. While the rest of the country is focused on the shiny chrome of new Cadillacs, Arthur Raymond is looking at something invisible to the naked eye. He is hunched over a metallurgical microscope, examining a sliver of steel that has been polished to a mirror finish. This is the final validation of his life's work, the forensic evidence of why his thermal tunnel changed history. Look at this. Joe, Arthur says, stepping back to let Joe Miller peer through the lens under the magnification. The steel doesn't look like a solid mass. It looks like a complex, interlocking map of tiny grains. In the old batch furnace shells, these grains were huge, irregular, and chaotic, like a wall built of mismatched stones. But in the induction-hardened steel, The grains are microscopic and perfectly uniform. It's called martensite, Arthur explains, his voice filled with a quiet intensity. By using the induction coils, we forced the steel to transform at a speed that didn't allow the crystals to grow too large. We didn't just make the shells faster, we made the metal itself structurally superior. This is why the barrels of our 150 hives didn't wear out, and why our shells never shattered on impact. The small observation had reached all the way down to the atomic level. The 90% reduction in production time was a result of a 90% increase in thermal efficiency. By targeting the molecules directly with electromagnetic waves, Arthur had bypassed the wasteful, centuries-old tradition of heating the air to heat the metal. Joe pulls back from the microscope, rubbing his eyes. You know, Artie, the boys at the Pentagon are still writing papers about us. They're calling it the logistical displacement. They say that for every hour we saved in the factory, we saved 1,000 lives on the line. Arthur nods slowly. He thinks of the steel rain over the Rhine and the endless crates of ammunition on the docks of Saipan. The war hadn't been won by a single silver bullet or a secret superweapon. It was won by the relentless, standardized perfection of millions of ordinary parts. As he begins to pack up his laboratory, he finds his old silver stopwatch, the one he used that first day at Republic Steel in 1941. It's scratched and worn, a relic of a time when the world was measured in the agonizingly slow minutes of an artisan's forge. He puts the watch in his pocket. The era of the artisan guess is over. The world has moved into the era of the calibrated pulse. Arthur Raymond, the civilian consultant who looked at a loaf of bread and saw a way to forge a nation's defense, walks out into the bright, post-war afternoon. He has finished his work. He has proven that in the modern age, the most powerful weapon in any arsenal isn't a bomb. It's the ability to master time itself. The silent vanguard of industry, June 1952. A high-tech manufacturing center, California. A decade has passed since the frantic nights in Cleveland, but the echoes of Arthur Raymond's small observation are now the heartbeat of the American economy. Arthur, now a senior consultant for the newly formed Department of Defense Industrial Board, stands inside a facility that looks less like a factory and more like a temple of the future. Before him sits the next evolution, vacuum-sealed induction furnaces. During the war, they had mastered the speed of heating. Now, they were mastering the purity. During the war, we just wanted the shells to be hard enough to explode, Arthur says to a group of young aerospace engineers. But for the jet engines and rockets we're building now, hard enough is a death sentence. We need alloys that can withstand temperatures that would have melted the old batch furnaces into slag. He points to a massive, gleaming cylinder where a turbine blade for a J-47 jet engine is being treated. There is no open flame, no soot, and no blacksmith's intuition. Instead, a computer-controlled induction coil hums at a frequency so high it's beyond human hearing. The metal transitions through its thermal phases with a precision measured in fractions of a degree. We cut the production time of artillery by 90% in 42, Arthur continues, his voice filled with a quiet pride. But the real victory was that we turned metallurgy into a predictable science. We decoupled human error from the manufacturing process. Because of that, we can now build machines that fly faster than the speed of sound. Joe Miller, now gray-haired and retired, but still Arthur's constant shadow, leans against a railing. You know, Artie, I saw a microwave oven in a magazine the other day. They say it uses waves to heat the food from the inside out, just like your coils did to the shells. They're putting your thermal tunnel in people's kitchens. Arthur smiles. The small observation from the bakery had come full circle. The logic of moving energy directly into the molecules had moved from the shell casing to the jet engine, and finally, back to the kitchen. It was a total transformation of how humanity interacted with the physical world. As they walk out of the plant, Arthur looks up at the vapor trail of a passing jet. During the war, he had been obsessed with the steel rain, the millions of tons of iron falling on the enemy. But now, he sees the steel ascent, the ability of a nation to rise, because it had learned how to master the very atoms of its own industry. The bottleneck of 1941 was a distant memory, a ghost of an era when men guessed at the heat of the fire. Arthur Raymond had looked at a loaf of bread and seen the key to a global empire of efficiency. He had proven that the greatest innovation doesn't always come from a new weapon, but from a new way of seeing the time it takes to build one. The Horizon of Precision, September 1960. The Smithsonian Institution, Washington, D.C. Arthur Raymond stands in the quiet, hallowed halls of the museum, his shadow lengthening across the marble floor. He is an old man now, mostly forgotten by the public, but the object he is staring at remains as sharp and lethal-looking as the day it was forged. It is a 150mm shell casing, cut in half to show the beautiful, uniform grain of the steel, the Raymond casing. Behind him, a young curator is adjusting the plaque. It doesn't mention Arthur by name. It simply reads, "The Arsenal of Democracy. How American Industry Outproduced the Axis." You know, the curator says, not recognizing the man beside him. This was the real secret weapon. Everyone talks about the atomic bomb, but it was these. We made so many of them, so fast, that the Germans thought we had found a way to grow them out of the ground. Arthur smiles faintly. It wasn't the ground, he says softly. It was the clock. He looks at the display. But his mind is back in 1941. He remembers the heat, the smell of sulfur, and the terrified look on Foreman Joe's face when they thought they couldn't meet the quota. He thinks about how one small observation about a bakery conveyor belt had rippled outward, changing the molecular structure of millions of tons of steel, and eventually, the very trajectory of the 20th century. The thermal tunnel logic had paved the way for everything from the Cold War arms race to the mass production of the transistor. By proving that high-energy physics could be harnessed for high-speed assembly, Arthur had helped birth the golden age of American manufacturing. The 90% reduction in production time hadn't just won a war. It had created the expectation of instant abundance that defined modern life. Arthur turns to leave, his footsteps echoing in the silent hall. Outside, the world is moving at a pace that would have been unimaginable to the blacksmiths of his youth. Transistor radios, jet airliners, and satellite communications. All of them built on the foundation of precision, speed, and the elimination of human error. He reaches into his pocket and feels the cold, familiar weight of his silver stopwatch. He doesn't need to click it anymore. The world is now running on the rhythm he helped establish. A rhythm where time is no longer a bottleneck, but a tool. As he steps out into the bright Washington sun, Arthur Raymond takes one last look at the Capitol dome. He was just a civilian, an industrial consultant with a sharp eye and a simple idea. But he had proven that in a world of giants and generals, sometimes the most devastating blow is struck by a man who simply refuses to waste a single minute.